Yeah.
Right. Okay, so thank you all for joining us for the fourth day of the conference. So it's really a pleasure to introduce Mohamed Majdoub from Imam Abdulrahman University in Saudi Arabia, and he will talk about the source type solution for the stable thin film equation. So please, Mohamed.
Thank you, Nader. First, I would like to thank Nader and Taj and all the organizers for this nice conference. I missed some talks at the beginning because I am traveling. This is a joint work with Slim Tayashi from Tunisia, and I will talk about the stable thin film equation. The equation is here, STF for stable thin film. So we have the first part is the standard thin film equation, and we have here a gravity term, or also a stabilization term. On here, HMZZ. With the complete fitting, we have here the homogeneous free boundary conditions. And of course, this is a free boundary problem. And the initial data here is the Dirac mass, or omega times the Dirac mass at zero. The n here is the mobility, is a positive real number. And the boundary is z minus z plus of t. The condition CLV, I call it CLV, the third condition, is of kinematic character. This means that the velocity of the thin film at the contact lines equals to the contact line velocities. About the physical motivation, STF, or the stable thin film equation, is relevant for surface tension dominated motion of thin viscous fields and spreading droplets. This was highlighted by Greenspan, and the gravity term, which is HMZZ, arises as a cutoff of van der Waals interactions. The first property of this equation, which is similar to the thin film equation, is the conservation of mass. So we can write the equation in terms of velocity v, which is equal to h to n minus 1 hzz, as follows. And using the boundary condition together with the CLV condition, we obtain that the mass is conserved. Because we try to solve the problem with Dirac mass at t equal to 0. So a way to do it is to look for self-similar solutions. Here we take, or we suppose that m equal to n plus 3, because in this case the equation enjoys a mass scaling, invariant scaling, which is given by this formula h lambda t z equal to this quantity. So the lambda behaves like t to power minus 1 by n plus 4. And it is known that self-similar means that H lambda equal to H for all lambda positive. This gives the form of our solution or our desired solution, HTZ, in this form. And the calligraphic H here is the profile. And of course, the source type means that our solution converges to omega delta in d prime of R as t go to 0. This implies that the profile also has the same mass, which is omega. So in the next slide, I will try to write the equation satisfied by the profile and then try to solve it. So the profile satisfies this ODE, this singular ODE equation, and we look for profile which is, of course, positive, which is regular, which is even, and with compact support equal to minus AA. This, of course, implies that the boundary will be given by this quantity. Looks like T to 1 by n plus 4. By rescaling and shifting, namely, we define this new profile h of x by this formula to absorb this constant here, 1 by n plus 4. Finally, we end with this system of equations, 1a, 1b, 1c, and 1d. The first equation is just the equation, this equation but written in terms of new profile. The condition 1b is just the complete wetting condition for the stable thin film equation. The condition 1c comes from the evenness of the profile. And finally, the condition 1d is the mass condition. So our aim is to prove that this problem has a solution which is regular and give the asymptotic of the solution of the profile H. So what can be said about this problem? First, for the standard film equation, TF, the first equation in our problem, 1a, reads 1a prime, which is hn minus 1 to h 3 derivative equal to minus plus x. Just in the equation 1a, of course, we remove this quantity which comes from the gravity term. First result by Bernice Pelletier-Williams in 1992 say that if we take the mobility n in the range 3 by 2, 3, then there is a unique non-negative solution H to all the problem. Moreover, we have the leading order term, which is given by this formula. So this quantity is the leading order term for the profile as x equals to 0. Here, the constant nu is equal to 3 by n, and since n is in this range, this nu is in interval 1, 2, and the constant a is equal to nu by minus 1 times 2 minus nu, and it is positive. Here, this leading order term, HTW, is the traveling wave. namely, it solves this problem. Of course, in the paper by Bernice Williams, they also investigate the case where n is less than 3 by 2 and n equal to 3 by 2 and obtain other similar results, but for other leading order terms. And also they showed that if n is greater than 3, then there is no solutions, of course, with compact support. And here, if you look at the theorem given by theorem of Bernice Williams, there is no condition 1D. There is no mass condition here. The reason is very simple, because in the standard thin film equation, we can reach any given mass positive by a scaling argument. And as we will see later, this is not possible for the stable thin film equation. Later, in 2013, Giacomilli, Otto showed that the profile H has this expansion. So they give expansion beyond the one given by Bernice Williams. So the expansion given by Giacomilli, Otto is equal, H is equal to here the traveling wave times to 1 plus a function v of two variables, x and x beta. Of course, x is the classical variable. And here we have a new variable, a new non-smooth variable, x beta, for some beta between 0, 1, and 1. And v is analytic near 0. Of course, v of 0, 0 equal to 0, and the derivative of v with respect to y on 0, 0 is negative. And the parameter beta can be understood by just by linearizing the profile h around the traveling wave, and in this case we obtain the equation p du equal to a of x, and p is a polynomial function, and the roots of p are -1, alpha, and beta. The root alpha is negative. We have -1, of course, and we have the root beta. And beta is in the interval 0, 1. Of course, the variable x to -1, x to alpha are ruled out by boundary condition. So the only new non-smooth variable in this case is x beta. For the stable thin film equation, there is a result by Beretta in 1997, again in the range 3 by 2, 3. There exists a non-negative profile H to the problem 1, A, B, C, and D. And moreover, the profile behaves like the traveling wave near 0. And in contrast with the thin film equation, in this case, for the stable thin film equation, there is no uniqueness, or the uniqueness, to be more precise, the uniqueness is an open problem. Maybe one can prove uniqueness in this case. We expect that uniqueness is true, but we don't. We have no idea how to prove uniqueness until now. Our aim here is to go beyond the regularity given by Beretta. So to find the next terms in the behavior of the profile. In particular, we show that the gravity term has an impact of the regularity near the boundary. And we expect that our analysis will be helpful in the local theory for the stable thin film equation. So now, what is the main result? The main result is stated here. For the range for the range 3 by 2, 3 for the mobility n, we have two parts in this main result. The first part tells us that we can construct a solution to the problem 1a, 1b, 1c. Here we call it h mu of x, which is equal to the traveling wave times 1 plus u bar of x, x beta, x gamma. And here the function u bar is the function of three variables, x1, x2, x3, and it is analytic near zero with these conditions. In particular, the derivative of u bar with respect to the variable x2 in 0, 0, 0 is negative. The parameter beta is the same as in thin film equation, but here we have a new variable, which is x gamma. Here we have the parameter beta is given by this formula, and because n is in this range, beta is positive, less than 1, and gamma is given by this quantity 2 plus 6 by n, and of course gamma is bigger than 1, so we have this order. And of course in the behavior near 0, the leading order term will be x beta. Here we see also that the gamma, the parameter or the variable x gamma is not smooth except for n equal to 2. If n equal to 2, of course gamma equal to 5. And this is the first part of the theorem. The second part, of the theorem, there exists mu bar positive such that the solution h mu bar satisfies also 1D, because in the first part we solve 1a, b, and c, and we have no mass here. In the second part, we recover the given mass for some parameter mu bar. Some comments here. We have a more precise here. I give a more precise form of the analytic function u bar x1, x2, x3 has the following shape, and we see here that the derivative with respect to x2 is negative in 0, 0. And of course, I said the result shows that there is two new non-smooth variables. Another important comment here is since there is no uniqueness until now for the stable thin film equation, so here we construct and we give asymptotic of the solution. So we are not expanding the solution given by Beretta. And finally, as I said before, we cannot reach any mass by scaling as in the thin film equation. So here we need the part 2 in the previous theorem. Now I will start the proof. And the first step on the proof is, of course, we linearize around the traveling wave. So we write the profile h equal to traveling wave times 1 plus function u of x, and we write the problem in terms of u as follows here: PD of u equal to all this quantity. So the first here is just the quantity or the term coming from the thin film equation. But here we have a new quantity and this variable x gamma. And of course, u of 0 equal to 0. Of course, here the d equal to x dx, and p is equal to this quantity. And an important remark here is since n is between 3/2 and 3, alpha is in -2, 0, and beta in 0, 1. So we have here, if we look at this equation, we have four variables: x minus 1, x alpha, x beta, x gamma, and of course the variable x. The x minus 1 and x alpha are ruled out by the boundary condition I said before. So there is only two new variables, and we call it y equal to bx beta and z equal to mu x gamma. And b and mu are positive parameters, and we are going to shoot on b and mu later. The function u of x, we write it in this form: u bar x bx beta mu x gamma. And in this case, if we apply the operator d to u, we can see that d of u equal to this bold d u bar, where this operator is given by this formula: x dx plus beta y dy plus gamma z dz. And in these new variables, our problem can be written as follows. So we have the same, but we replace u by u bar and d by d bar, and here we have the variable z, and we have the condition u bar and the partial derivative of u bar with respect to y in 0, 0, 0 equal to 0 minus 1. So what is the strategy of the proof now? First, we solve the linear problem, and we obtain some estimates. Then we use them to solve the nonlinear problem using a fixed bound argument. At this stage, we obtain a local solution. We call it HB mu of x in this form. Then we shoot with the parameter b to obtain a solution of 1a, b, and c in the interval 0, 1, because in the local solution we have a maximum local solution, and we don't know if we reach the whole interval 0, 1. And finally, we conclude by shooting with the parameter mu to obtain the mass. So the linear problem, I will not concentrate on the linear problem because it is almost clear. So here just a notation: the SIP norm in the Q epsilon is given by this notation, and of course the n naught. So a lemma here say that if we have a smooth function f bar of 3 variable x1, x2, x3, and f bar partial derivative of f bar with respect to the second variable is equal to 0, then we can solve the linear problem d bar minus lambda v bar equal to f bar by this formula. And this solution, we have an operator t lambda, which solves the linear problem, and the t lambda commute with the operator d bar. And we have also some estimate here on the solution. So the condition here is the parameter to solve this linear problem. We have to suppose that the parameter lambda is less than beta. Of course, we can apply, but here just why we take here in the first variable epsilon squared and then epsilon squared. This is can be seen just by saying that if we have a smooth function f bar which vanish at 0, 0, and also the partial derivative with respect to second variable also equal to 0, then f bar of x, y, z is bounded by x plus y squared plus z, and hence the variable x, if the variable y scale like epsilon, the variable x and z must scale like epsilon squared. And this information can be seen just by writing f in this form, which is his in footnote. It is not difficult. So if we apply the above lemma and we compose the different operator t alpha, t minus 1, t beta, then we can solve this linear problem p d bar u naught bar equal to f bar, and obtain this estimated this norm 1 is less than this norm 0, and here we define the norm 1 and norm 0. So then for the local existence, so here our problem, so here we write another time our problem in this form, and here f bar u bar is given by this quantity. This problem can be written as a fixed point equation in this way. U bar equal to minus x2 plus t f bar u bar. We write this as calligraphic t of u bar. And of course, here we have to show that this equation has a solution. So we introduce here since we look for analytic solution, we cannot work directly in the analytic space because we have a problem with completeness. So we construct a C-infinity solution, and then we show that this solution is analytic. So it is not direct argument. So for this reason, we consider this space as KLM for KLM in N, which is the space of the function which is of class CK plus LM plus 3 in the cube Q epsilon, and with this condition, and then this norm is less than epsilon. What is this norm? This norm is equal to the norm 1 plus this term, and we add this term because we need completeness of the space. We need the completeness because the norm, just the norm 1, we have the weight in the SIP norm, and this make the space not complete. In this way, this space becomes complete. becomes complete, and we remark that if we take U bar in this space SKLM, we can see that the second term F bar U bar together with the partial derivative with the second variable of F bar U bar equal to 0. Then we show that this operator is a contraction in this space SKLM for epsilon small. And here we show these estimates, and we stress that we have, of course, we have in this inequality some constant, but doesn't depend on K, L, or M. So it is uniform with respect to the parameter K, L, and M, because next we will use this fact. To prove these estimates, we use just some arguments, lower order norms and algebra properties, and also Monori estimates. So I will don't focus on this. So we skip these details. Now we claim that for epsilon small in 0, 1, we can find a function U bar which is analytic in Q epsilon and solves our problem. The argument is not difficult here because, as I said before, all the estimates are independent on of K, L, and M. And also another argument is this: the metric spaces SK, L, M are nested as K, L, M increase. So there is a unique fixed point which is infinity, and the Taylor series converges, and the error terms converge to 0, and we can obtain that the solution is analytic. It is just technical. Now, how to reach the interval 0, 1? If we, until now we have constructed the initial solution to 1A, 1B in the following form: H B mu, and this solution is defined in this interval, and of course by ODE arguments we can extend the solution smoothly on the maximal interval 0 x star b mu. The main claim here. So here we fix the parameter mu. So here we work for mu fixed. So we claim that by shooting argument on the parameter b, we can find b bar mu such that the function h b bar mu satisfies 1a, 1b, 1c, of course, on the interval 0, 1. And moreover, the derivative is positive on the interval 0, 1. Some element of the proof. First, by comparing our solution, our local solution HB mu to traveling wave, we obtain that the derivative is positive for x small, and also we obtain some monotonicity in B, which gives that the maximal time of existence goes to 0 as B goes to infinity. These two arguments allows us to say that the derivative must vanish somewhere. So the derivative of HB mu must vanish somewhere. Now we can define, with this, we can define what we call here V bar of mu, which is the infimum of all B non-negative, such that the derivative is equal to 0 for some x. So this set, we call it B. And how to conclude? By continuous dependence on B and monotonicity, we can prove that B bar mu is positive and belongs to B. It is an infimum. And to conclude, we have to show that x B bar mu bar equal to 1. What is this bar? It says for all B on B, x B bar is the first 0 of the derivative of h B mu. By contradiction, if we assume that x bar B bar is less than 1, then the derivative of h B bar mu will be negative near this point in the right neighborhood. And since we know that the derivative is positive on 0 x bar B bar mu, then we deduce that this property will be satisfied by also h B mu for B near B bar mu. So h B mu, the derivative will be positive and negative somewhere. And this yields that we can find B between 0 and B bar mu, such that the derivative of h B mu vanishes somewhere. And of course, this contradicts the definition of B bar mu as the infimum of B, of the set B. So here we arrive that we can conclude, and this B bar mu is the desired B in the clay. So we define now h mu by this function equal to h B bar mu. And here, of course, I said before, the parameter mu is positive and fixed. So now, until now, we have constructed a solution h mu which solves 1a, 1b, 1c. So this is the part 1 of our main result. Now, how to reach the mass? Because I said before, we cannot, by scaling argument, say that we can reach the mass. The mass cannot be reached by a sample scaling argument as for the thin film equation. So we have to prove that we can satisfy the condition 1D for some mu positive. So this is the main difference with respect to the thin film equation. So we claim that there exists mu bar positive such that h mu bar satisfies also 1D. Namely, we have this integral equal to this quantity. This is exactly the mass condition. How to prove this claim? So we define this function of mu, m of mu equal to this quantity. So just we move this term in the right hand side in front of this integral, and we have to show that this function m of 0 infinity is equal to 0 infinity. So if we show this, of course, any given mass omega positive can be reached. So by continuity argument, and since m of 0 equal to 0, it is enough to show that m of mu j goes to infinity as j, and j goes to infinity for some sequence mu j. So we will show that there is some sequence mu j satisfying this property. And this will be done in 3 steps. The first step is the following. So here we define the ith calligraph mu of y by this formula. This is what we do in the first, because in the first we have the profile, this profile, and then by scaling and shifting, we define a new profile. Here we need to work with also with the old profile. So this is the relation between the 2 profiles. We use some estimates in the paper of Beretta, and we obtain that the second derivative of h mu in 1 is less than some constant Cn times square root of n plus 4 times h mu of 1 to the power 1 minus n by 2. And also, we show that the maximum between these 2 quantities is greater than dn. Cn and dn are positive constant depending only on n. So to show these 2 estimates, we use mainly the argument in Beretta, in the paper by Beretta. The next step is to we define this quantity alpha of mu. Here we have h mu of 1, and here we have mu to 2 by n plus 4. Of course, this is just a constant on n, it doesn't matter. And we claim that the supermum of alpha mu is equal to infinity for mu positive. Why? Because if not, by using the above estimates, we should have 1 is less than mu to the power minus n by 2 n plus 4 for all mu positive. And of course, this is a contradiction. By using this information that the supermum of alpha mu for mu positive equal to infinity, we deduce that there is some sequence mu j such that what we call here alpha j, which is equal to alpha of mu j, goes to infinity as j goes to infinity. And we will use this sequence alpha j in the next step. So the step 3 we will use a comparison argument between the profile. So we compare here the profile to the second order differential equation, which comes from the leading order terms in the equation. So we define Vj, which is a function of y, equal to Vj of y, is the solution of this problem. So here we have the alpha j. We have the constant Cn, which is given by the above estimates. And the initial condition is Vj of 0 equal to alpha j. And the derivative is equal to 0. Of course, we can solve this problem, and the solution is given by this formula. Here we have the hyperbolic cosine. And by comparison argument, we can see that the profile calligraphic h mu j is greater than the solution Vj. And by this argument, we can deduce that the mass, or the m of mu j, which is equal to this quantity, 2 times this integral from 0 to aj, is greater than this quantity, which goes to infinity as j goes to infinity. So the m mu j goes to infinity. And of course, a continuity argument enables us to conclude that any mass can be reached. Some concluding remarks. Finally, what can be said for n less than 3 by 2? Until now, we have no similar results. For example, for n equal to 3 by 2, the constant a appearing in the traveling wave is equal to 0. So, of course, for the thin film equation, we know what are the leading order terms for these cases. For n between 0, 3 by 2, and for n equal to 3 by 2. For n greater than 3, we have no solution. And what can be said for the unstable case? But because all these arguments are for the stable case. So the unstable case, or the unstable regime, is this equation. So here we have minus instead of plus. If we look at our proof at all steps, we can see that with our approach, we can construct a solution for 1a and 1b. There is no problem. But to satisfy 1c and also 1d, we use some comparison arguments, and here we need the sign plus. We need the sign plus. So we don't know how to do in the unstable regime, and more than that, in fact, it seems that as pointed out by Witilski, Bernov, and Bertozzi, that for the unstable case, the problem 1, we can construct a regular solution to the problem 1 for mass omega less than a critical mass, which is given by omega c equal to this quantity, 2 pi square root of 2 by 3. So here we have a problem with mass for the unstable regime. And also, finally, I can also say something about weak solutions for the problem. In fact, weak solutions for the problem for the stable regime was obtained by, for example, Bertozzi Puch, and also Beretta, Dal Basso, and also there is some results about the competition between this part, the thin film part, and the porous medium part, which is HMZZ. So there is a competition. There is a competition in terms of N and M. If we have mobility N, of course, positive, and we have M, which is also positive. So we have two parameters, N and M. And a question is to study the competition between two terms, the fourth order term and the second order term here, or the thin film term and the porous medium term. So there is some results in these directions, and I have no time to discuss them. Finally, I will congratulations to Professor Nader Masmoudi for the King Faisal Prize on Mathematics for 2022. So thank you, Nader, for your contribution in mathematics.
I say thank you for him. Go ahead, sorry.
And thank you all for your attention.
Thank you, Mohammed. It was a very nice talk. He had to leave for personal reason. He will be back soon. Nader, so thank you so much for this very nice talk. Are there any questions or comments in the audience? Okay, just a small question, Mohammed. Can you go back and explain us again? I didn't really. Why do you need the analytic regularity for the? At a certain, yeah. Do you have a loss of, or was it just?
It is said here. And confirmed later by Kamil Legnan, Otto, and Kiefer, that the analytic regularity gives us the beyond the reading order term and is helpful to construct the weighted suburban spaces in which we construct a local solution. So we use this expansion to construct the weighted spaces in which we can perform local existence for the problem.
Okay.
I have one question, please.
Yes, please.
Thank you, Mr. Majdoub, for your presentation. For unstable case, does the profile preserves for unstable case?
For the unstable case, yeah.
Yes, yeah. Does the profile preserve the same formula as the unstable case?
Does the
profile?
The profile.
Yes.
The profile is the same as the stable case, but this was given in the paper by Beretta. But the only difference is in the unstable regime. We have to suppose that the mass is less than some critical mass. But if we look just the profile, the reading order term is the same, at least for the range of mobility n between 3/2 and 3, because all the work is for this range of mobility.
Thank you.
Okay. Are there other questions or comments?
Well, I don't have a question, but I would like just to say hi to Mohammed and thank you very much for this talk. Salim is speaking.
Thank you, Salim. Thank you. How are you, Salim? How are you?
Very good, thank you. I'm missing that place, of course, but everything is okay. Give my best to the friends over there.
Thank you. Okay.
Okay, if there are no other questions, thank you again, Mohammed, for the talk. And we all meet again at 2:30 for the next talk.
Okay, thank you, Tej. Thank you all. Thank you, Nader. Thank you all.